Welcome to podcast 2 on chapter 20. We'll start today with electromotive force. I know in podcast 1 I had briefly touched on it, but today I'm going to go over electromotive force and cell potential, which is the same thing, in terms of spontaneity of reaction in voltaic and electrolytic cells. So let's start with slide 13. And electromotive force is what drives the flow of electron. Electrons flow from higher EMF to lower EMF. Just like gravity makes water fall from top to bottom, similarly, electromotive force makes electrons flow from higher to lower cell potential. So in case of voltaic cell, you had seen there was anode which had higher potential or more electrons, and you had cathode which had lower potential or lesser number of electrons, so electrons flowed from anode to cathode. Electromotive force or cell potential is written with uppercase E and subscript cell for the overall cell. A cell generally is made up of two half cells, and two half cells refer to oxidation half and reduction half cells. The unit of cell potential are volts, and 1 volt is 1 joule per coulomb. And standard conditions are 25 degrees, 1 atm, 1 molarity. So standard cell potential is cell potential measured at 25 degrees, 1 atm, and 1 molarity. Cell potential is unique to each set of two half cells that are involved. So for copper zinc, you'll always have the same cell potential. If you have silver copper cell, then you will have a different cell potential as compared to zinc copper. But for silver copper, you'll always have the same potential under similar conditions. This is picture of Coulomb. In his honor, the unit of electromotive force is called Coulomb, which is, let's go back on it again. Coulomb is a unit for measuring the charge. And the way Coulomb is connected to volt is 1 volt is 1 joules per Coulomb. Moving on to reduction potentials. So you know a substance can either undergo oxidation or it can undergo reduction. So if a substance undergoes reduction, we call the potential as reduction potential. And how you have two half cells in a voltaic cell, right? We haven't done electrolytic cells yet, so let's focus on voltaic cells for now. So there are two half cells in a voltaic cell, reduction half cell and oxidation half cell. So when you're talking about the cell potential, it's what is the overall potential. And cell potential, this formula you'll need to remember, guys, is cell potential is the difference of reduction potential of anode reaction and reduction potential of cathode reaction. Please note two things. You are measuring reduction potentials for both reactions. The reduction reaction that's happening at cathode and the oxidation reaction that's happening at anode. Remember, anox red cat? So even though oxidation is happening at anode, you're still writing its reduction potential. You don't need to flip it around. That's why there's this negative sign that takes care of it. And this is where kids get confused. So I'm emphasizing it, and I'll reiterate it with an example. So this is a hydrogen electrode, standard hydrogen electrode, where hydrogen gas is bubbled at 1 atm pressure on a platinum electrode, which is a neutral or inert electrode, and the molarity of hydrogen ion is 1 molar. And the reaction that happens is two hydrogen ions accept 2 electrons to make 1 hydrogen molecule, and the potential of this reaction by convention is taken as 0 volts, and we call that 0 volts. and we call this as standard hydrogen electrode, and every other element's reduction potential is measured against hydrogen. So you have zinc changing to zinc ion, copper ion changing to copper. First, if I were to ask you what is the cell potential for this reaction, the first thing that you have to do is identify cathode reaction and anode reaction. What do you think is happening to copper? When copper ions changing to copper, it's accepting electrons, and accepting electrons is reduction, right? And then when zinc is losing electron to form zinc plus, it's undergoing oxidation. So when you start calculating cell potential, it will be reduction potential of the reaction occurring at cathode minus reduction potential of reaction occurring at anode. Okay, so what is happening at cathode? At cathode, copper 2 plus is converting to copper, right? So you will be writing reduction potential of copper here minus, you'll be writing reduction potential of zinc reaction here. Okay, and you can see there is a big chart. It is actually at the back of your periodic table that you've been using on your test and quizzes, and that chart is called a reduction potential chart. I'm going to go over it with you in class. And this chart is listed from highest to lowest reduction potential. The higher the positive value of reduction potential, the greater is the reduction potential. So plus 3.4 reduction potential is higher than negative 1.1. Right? So the more positive reduction potential, the more is the tendency of something is to be reduced. So something with higher reduction potential, will it be a good oxidizing agent or a good reducing agent? You are right. Something with higher reduction potential will have a tendency to get reduced itself, so it will oxidize something else. So it will be a good oxidizing agent. Now in this reaction, you substitute the values. Guys, I do want to emphasize here, you do not change the sign or anything, you just read it off the chart. So when I read it off the chart as it's sitting in front of me, the reduction potential of copper is 0.34 and the reduction potential of zinc is negative 0.76 from the chart, and I just put it like that, and that gives me cell potential of positive 1.10. Whenever the cell potential is positive, it means reaction is spontaneous and it's a voltaic cell. For positive cell potential, delta G will be negative because reaction is spontaneous. The other thing you need to know is if for the reaction zinc plus Cu2 plus gives you Zn2 plus plus Cu, cell potential was 1.10 volts, and if you times it 2, cell potential will not double because cell is in per unit charge. So as you double it, the charge doubles as well, so the ratio remains constant. Unlike delta H or delta G, where you double a reaction, the value doubles. Here you may double a reaction, but the value does not double. This is very important because we'll be using it towards the end of the chapter, so don't forget this. However, if you have more moles, it means reaction will go for a longer time before it runs out. So how do you use standard reduction potential table? I briefly went over it. So the strongest reducing agent will oxidize easily or will have the lowest reduction potential. And predicting if someone will reduce someone, you need to look at its reduction potential, right? So any metal that's above any other metal has a higher reduction potential, means it will be able to oxidize the metal below it, because it will be getting reduced itself, so it will be accepting electrons, so the metal below it will be giving electrons. And remember, in single replacement reactions we had that list where I told you any metal above any metal can kick it out from a pair and take its place. Guess what that activity series was based on? You are right, that was based on reduction potentials. Now moving on to spontaneity of redox reactions. How do we predict which redox reactions will go on their own and which you'll have to give energy to? Spontaneity is very important because as you know, a lot of these electrochemical cells are used for making energy, so we need to know which one can convert chemical energy to electrical energy. Spontaneity of redox reactions is determined by Nernst equation as well, which you've done in the previous chapter, but we do have another equation here which came from Faraday's laws. Michael Faraday did a lot of work in electrochem, and that equation is absolutely must remember equation. It's delta G0 is negative NFE0. Okay, and that equation is very important because it connects Gibbs free energy delta G to the cell potential, and because of the negative sign here, you can see the higher the positive value of E0, the lower will be delta G0. So you absolutely must remember this equation. In this, delta G0 standard Gibbs free energy, N is moles of electron transferred in that redox reaction. F is a constant called Faraday's constant. Its value is 96500 coulombs per mole of electron. So if there are 2 moles, then you're multiplying 2 by 96500. And E0 is the cell potential. Now you can see here from this negative sign, as E0 increases, delta G0 decreases. So under standard conditions, we know what the cell potential is, or we can calculate. But what if it's a non-standard condition? Remember Nernst equation from last chapter? Delta G is delta G0 plus RT natural log of Q. Now we're going to use Nernst equation with E0, and if we substitute delta G with NFE0, the form of Nernst equation we get is this: E is equal to E0 minus RT over NF natural log of Q, where E is cell potential under non-standard conditions, E0 is cell potential under standard conditions, R is 8.314 joules per mole Kelvin, T is temperature in Kelvin, N is number of moles, F is a constant, natural log of Q, Q is reaction quotient, products over reactant for aqueous or gaseous systems. So Nernst equation can help you convert standard cell potential into the cell potential under reaction conditions. Absolutely important equation to know. Now at equilibrium, you know delta G becomes 0 and Q becomes K. So if we substitute the values in here, put 8.314 for this, and put standard condition like 25 degrees Celsius or 298 here, and put Faraday's 96500 and change natural log to log, the equation you get is E0 is 0.0591 over N log of K. And then this is another important equation to remember. This is at equilibrium, and at equilibrium K becomes equal to 1. You can see the relationship between delta G, K, and E0 in the next cell right here. So delta G0 is negative, then K is greater than 1, E0 cell is positive, and reaction is spontaneous. At equilibrium, delta G0 is 0, K is 1, E0 0. And for non-spontaneous reaction, delta G0 is positive, K is less than 1, and E0 cell is negative. And this is a very important slide which kind of connects K, delta G0, and E0, the important quantities in chemistry, to each other. The relationship between delta G0 and K is delta G0 is negative RT natural log of K. So you can convert between delta G0 and K using this equation. You can also calculate K, guys, using product over reactants to their moles at equilibrium, right? Or you can calculate Kp or Kc by using partial pressures or concentrations. K equilibrium and E0 cell is by this equation, or you can even use E is equal to 0.0591 over n log of K. So they are related to each other through that. Delta G and E0 are related to each other through delta G0 is negative NF E0. So you can interconvert between these by using these equations. And remember, Nernst equation is used to convert standard cell potential to non-standard conditions, or standard Gibbs free energy to non-standard Gibbs free energy, as we did in last chapter. And then cell potentials are important to us because our body, human body, the pumps, potassium, sodium pump and stuff are built on membrane cell potential. And I will end this podcast here, and I will do the electrolytic cells in the last podcast, which will be podcast 3 for chapter 20. Thank you for listening.